The Diels-Alder reaction is an example of a pericyclic reaction. Pericyclic reactions have a concerted mechanism, meaning that all of the bond making and breaking occurs simultaneously. Furthermore, pericyclic reactions have a cyclic transition state. In the Diels-Alder reaction, a conjugated diene and a diene-loving reactant, known as the dienophile, unite to form a cyclohexene ring. The diene is typically the more electron-rich reactant. As such, you can envision it attacking one of the carbons of the dienophile. The dienophile simultaneously attacks the opposite terminus of the diene, pushing the remaining diene pi bond to a new location. This results in the formation of the cyclohexene ring. Several significant things happen during this transformation. Two new carbon-carbon sigma bonds are formed. They are shown in red and in green. A six-membered ring is also formed. And finally, 4 carbons are rehybridized from sp2 to sp3, meaning that these 4 carbons could conceivably become stereocenters if they were substituted accordingly. For the Diels-Alder reaction to be possible, the diene must be able to adopt the S-cis conformation, in which the terminal alkene carbons reside on the same side of the central single bond. In the specific example that follows, the electron-withdrawing ketone substituent renders the dienophile electron poor so that the reaction proceeds more readily. It's useful to note that many different electron-withdrawing groups can be employed in this reaction, and that includes carboxylic acids, esters, nitriles, and others as well. The result is again a cyclohexene ring, this time bearing the ketone substituent. A stereocenter has also been formed in this reaction. Since the diene and the dienophile are both trigonoplanar or flat at their reactive centers, addition can occur from either side of the dienophile to push the ketone up or down. The result is a racemic mixture of enantiomers. When both the diene and the dienophile are unsymmetrically substituted, regiochemistry becomes an issue. For instance, in this reaction, there are 2 conceivable ways for the diene and the dienophile to combine, and these would lead to different products. Examining the resonance structures of each reactant will illustrate the preferred combination. Let's look at the diene first. The diene has an electron-donating methoxy substituent. A lone pair of electrons from the methoxy group can be pushed into the diene to place delta minus character at one terminus of the diene. Conversely, the dienophile possesses an electron-withdrawing ketone, which can draw electron density out of the carbon-carbon double bond. This places partial positive character at one end of the dienophile. The diene and the dienophile will preferentially approach one another with the termini having complementary polarities. In other words, the delta minus and delta plus termini are attracted to one another. When aligned this way, a single regioisomer results. However, since a stereocenter is formed during the reaction, both configurations are possible at that stereocenter, and the product is a racemic mixture of enantiomers. the concerted nature of the Diels-Alder reaction has stereochemical ramifications. Since the Diels-Alder reaction is concerted and all the bond making and breaking happens at once, the reaction is stereospecific. This means that a particular configuration of the reactants will lead to a particular configuration of the products. For instance, in this example, the dienophile bears two ketones that are cis to one another, and that cis arrangement is preserved in the product. Since all the bond making and breaking happens simultaneously, there is no opportunity for any change in the orientation of the ketones relative to one another. In this case, the product happens to be meso and therefore has no enantiomer. If we examine a similar reaction in which the ketones have the trans orientation, we see that that is also preserved throughout the reaction, so that the ketones are trans to one another in the product as well. But in this instance, the product has no internal plane of symmetry, and so a racemic mixture of enantiomers is formed. A second facet of the stereochemistry of the Diels-Alder reaction is the preference for endo addition. In the reaction shown below, a cyclic diene is used. Consequently, the product contains not just one ring, but two, and this makes it a bicyclic compound. When we draw that bicyclic product in a more three-dimensional perspective, it becomes clear that the ketone may be placed closer to the one-carbon bridge or closer to the two-carbon bridge. When the substituent is closer to the shorter bridge, the product is known as exo. However, when the substituent is closer to the longer bridge, it is termed endo instead. There is an electronic preference for the endo product, and this preference results from additional orbital overlap that occurs between the substituent, the ketone in this case, and the diene during the transition state of the reaction. When the substrates are placed so as to allow this additional orbital overlap, you'll notice that the ketone ends up closer to the two-carbon bridge than it would be to the one-carbon bridge. And this is the genesis of the endo selectivity. Consequently, this pericyclic reaction can be drawn with more stereochemical detail to illustrate the formation of the endo product. And there are multiple three-dimensional perspective drawings that we can use to convey this outcome. It's also important to make note of the fact that both endo enantiomers will be formed. We can derive the structure of the other endo enantiomer by drawing the mirror image of the first compound we drew. And if desired, we could rotate this mirror image 180 degrees to place the molecule in an orientation similar to that of the original molecule. In summary, the Diels-Alder reaction is a pericyclic reaction in which a diene and a dienophile are joined to yield a cyclohexene ring. The regiochemistry of the reaction is determined by complementary polarity of the reactants. Furthermore, the reaction is stereospecific and exhibits a preference for endo addition. The preceding has been an excerpt from the book Introductory Organic Reaction Mechanisms, a color-coded approach to arrow pushing. If you found this video to be helpful, you may be interested in the complete book, which is available in ebook format from Scribd, in paperback from Amazon, and in paperback at a discounted price from Lulu.